Hey class, welcome to Unit 3. And this particular unit is on normal distributions, which are the most important type of distribution that you typically will study in statistics. And while not all distributions are these bell-shaped symmetric distributions like normal distributions are, I mean, think about it. We've learned skewed distributions, left skewed, right skewed. You can have bimodal distributions with two peaks, but bell-shaped unimodal with one peak in the middle are extremely important in the study of statistics and the types of hypothesis tests that you'll learn later in the course. Many of them are founded on an assumption of the fact that we're dealing with approximately normal distributions. So let me first go ahead and pull up the discussion so that I can help y'all with that. All right. So for the Unit 3 discussion, you will be calculating probabilities within normal distributions, and you'll start out with a blank Excel worksheet. Open a blank Excel worksheet, go to cell A1. So I'm coming over here and type the following, and it's very important that you realize you have to start with an equal sign right here. This is actually an Excel function that allows you to generate a random number. So what that means is most of you all will get different numbers in the discussion, which is good. It's going to be important to see the variation in the different values that you get and the different conclusions that you all make. So I'm going to start with an equal sign here in A1 and then capital RAN, and it'll even bring up, once you start typing a few letters, you can even see where it says ran between right here. So I'm just going to click on that. And then what we want is to generate a random value between the numbers 57 and 76. So I've got the parentheses already open. I'm doing 57 comma 76, close parentheses, and then press enter. And my number was 68. Whatever y'all are going to get, you're going to share with us. Now, because I do not want to work out the actual discussion question, I'm going to leave that up to y'all in the discussion this week. Then I just wanted to show the Excel screen there just to show you how to generate the value in case you had trouble with that. So let me go ahead now and get out of the Excel screen here. And let me bring up, I'm going to show y'all how to do some of these calculations. Okay. There is a website. Let me pull this up so you can catch the website if you need it. All right. Here is the website that you may want to get this link here. You're going to be wanting to most likely use it for a lot of the homework questions this week. It is a website that allows you to calculate probabilities for normal distributions with z-scores. And that's a big part of what you'll be doing in the homework and also what you'll be doing in the discussion. The sort of old traditional way of calculating probabilities with normal distributions is to use a z-table. Although now with technology advancements, it's, in my opinion, a little bit obsolete to sit there and rely on reading these messy, tedious looking tables to get probabilities, because there's so much technology now that will do it automatically. Excel will do it. It's just not quite as user-friendly and easy to navigate through as some other websites that are out there. And that's why I thought I would share this one with you. So hopefully you've got this link now. Otherwise, you pause, get that link so that you can use this to do some of the calculations. And now let me pull up that particular website so that I can show y'all how to use it. All right, so you've got the website on your screen now. And I have scrolled down to the part of the website, like here's the top of the website. I just scrolled down because you're going to want to get to the section where it says areas under the normal distribution. All right, first off, there is a formula for calculating a z-score, and it is z equals If I wrote it in words, it would be taking the value that you're trying to convert minus the mean of the distribution that will typically be provided for you and divided by the standard deviation. I'll just put SD for standard deviation. You may also see the Z formula written out with symbols. And if the symbols that are used are population symbols, then it will look like Z equals X for your value minus mu, which is the Greek symbol for population mean, divided by sigma, which is the symbol for population standard deviation. So like in the discussion, you'll be doing calculations involving male heights, female heights. Well, it is assumed that the mean and standard deviation that they are giving you in that problem are the mean and standard deviation of the entire population of adult males or the entire population of adult females. And that's why in that scenario, they would, you would most likely use the population symbols. But in your discussion post, you're not going to have to worry about pasting the symbols and stuff. That you'd have to go online and retrieve those symbols somewhere. So don't stress out about that. You can actually write out the formula in words. All right, so let me give y'all a just hypothetical scenario so I can begin to show y'all how to use the website and how to do these calculations. So let's suppose adult males have and instead of height, I'm just going to look at weight. Let's suppose adult males have a mean weight of 170 pounds. So mean of 170 and a standard deviation of 15. Well, what that means we would be looking at is if we are told that adult male weights are normally distributed or approximately normal, because remember, like I said earlier, not every distribution in life is normally distributed. A lot of biological ones are, and things like that, some in business and stuff. But just keep in mind that we need to be told that we're dealing with something that's normally distributed. So if adult male weights are normally distributed, we can approximate the distribution of their weights to look like this. That's a picture, rough sketch of a normal distribution. The mean of the bell-shaped symmetric normal distribution is in the middle. It's symmetric. So that's where the value 170 would be along the horizontal axis. And if the standard deviation is 15, what we need to realize is if we split the right-hand side up into roughly around 3 standard deviations and did the same for the left side, then when we're dealing with normal distributions, almost all of the observations, all of the values should be found within 3 standard deviation units of the mean in both directions though. So like if I take the standard deviation of 15 and add 15 to the mean, that would put me at 185. Add another 15, that would put me at 200, and add another 15. On the other hand, if I go the other way and do 170 minus the 15, then I'm at 155, and then 155 minus the 15, I'm at 140, and then 140 minus the 15, I'm at 125. So if, in fact, these were the true mean and standard deviation of weights of adult males, we would say that most males have weights between 125 and 215. Now, realize these may not be accurate numbers. All right, so that would be a picture of what we're looking at when we get this kind of information. Although you shouldn't really have to write all of this stuff out when you're doing just basic z-score distribution problems. Now, I will tell you there may be a problem or two out there that talks about the 95% rule for normal distributions. If it mentions the 95% rule, then what you want to realize is that when you go out 2 standard deviations from the mean in a normal distribution, then you should be capturing roughly 95% of the data. So like in this case, I ought to be able to say then that if I go out, so let me go out 2 standard deviation units to here, and this is 2 standard deviation units away from the mean, and then 2 standard deviation units that way, then I should be able to conclude that roughly 95% of male weights because I'm going out the 2 standard deviation units. So for the 95% rule, I would be able to conclude that roughly 95% of adult male weights are between a 140 and a 200. That would be if you get a question that asks for the range of roughly 95% of the values. So be on the lookout for something like that out there. All right, but let's actually, let me illustrate how to use the z-score calculation, and I'm going to show you over here on the right-hand side visually what it means, but then also show you how to use the website, because like I said, the website is going to be much easier to do area calculations and probability calculations this week. Okay, so let me erase this down here. All right, so suppose I happen to get a weight of an adult male of, say, 192. Just imagine an individual adult male who weighs 192. All right, well, what that means then is my X is going to be 192 because the X stands for the individual value. So to use the z-score formula, I would do z equals, I would take the 192 minus the mean of 170 divided by the standard deviation of 15. Now, if you put this in a calculator, you got to make sure that you press enter after you do the numerator. Otherwise, order of operations would mess you up because the calculator would try to divide first. So like in my calculator, I'm doing 192 minus 170 equals, though, and then dividing it by the 15. And usually we round z-scores to 2 decimal places. So I'm getting a z-score of roughly 1.47. You will be asked questions in your homework, excuse me, questions in your homework about what that means. Well, a z-score represents the number of standard deviation units away from the mean. And so if I were to draw just a basic z-score distribution, which is referred to as the standard normal distribution, then here's what the z-score distribution looks like. The z-score in the middle would be a 0. So like this is called the standard normal distribution, and that just means assuming all values are converted to z-scores. So the standard normal has a z-score of 0 in the middle, and then we put the 1, the 2, the 3, and the so forth, -1, -2, -3. So all a z-score really is all it means, or I don't want to say all it means, it's important, but what a z-score means is it is a number that is telling you how many standard deviation units away from the mean your value is. And it's also telling you whether your value is above average, because if you get a positive z-score, it means your value is above average. If you get a negative z-score, it means your value is below average, because average is a z-score of 0, right in the middle. All right, so what I can tell from this calculation about a adult male that weighs 192 pounds, that male's weight is 1.47 standard deviation units above average because it is positive. And you'll have little drop downs in your homework where you click above average, below average, and that kind of thing. So this male's weight is 1.47 standard deviation units above average. That means, if you kind of imagine this graph right here, it would be falling in about right here because that's almost halfway between 1 and 2 standard deviation units. So you will be using this website and answering questions about what's the probability of getting a weight even above that. What percentage of males even have weights above 192? Or what percentage of males have weights below that, where you would be finding this probability? So probabilities and percentages basically mean the same thing, and that's where this website is going to come in handy. So let's go over here and I'll show you how to use it. So let's suppose it really is the same information. I would need to change my mean over here to the 170, change my standard deviation to the 15, And you get a picture of what I had already drawn earlier, where it shows the 170 in the middle, and it shows the entire distribution with most weights between, it doesn't show the 125 over here and the 200. I forgot what the other weight was, 200 something. It doesn't show those, but it's implied that those weights can get that far out. Well, if I want to find the percentage of male weights above 192 pounds, then I would click the above radio button and change this 63 to 192 and then press enter. And there it shows the shaded region that I had shown over here in the green shaded region, showing the exact same thing. I just showed how to draw it by hand, and then I'm showing you how the website will do things for you. Well, if we come down to the area probability box, we see that that is telling us that roughly 7.12% of males have weights even above 192 pounds. If I had clicked below and put in the 192, press enter, then it goes in the opposite direction, and realize the leftover, like if I did 100% minus my answer for above the 192, I should get the answer below. Because if you take the percentage below the 192, like if you come over here and look at the blue region, and you add it to this green region, that takes up the whole area under the entire curve, and that's 100%. So it's just now going in the opposite direction and doing 100% minus the previous probability to give me what's to the left. So you would definitely want to make sure that you pay attention to whether the question wants above or below. You can even find in between. I mean, suppose I wanted the percentage or probability of weight, male weights, between, say, 165 and 192. Press enter. It's showing that on the graph and telling me that roughly 55.93% of adult males have weights between 165 and 192. And, also pay attention to the format of the question. Like, does it want answers in probability, like to decimal places? In this case, suppose it wanted me to round to 3 decimal places. I would just put 0.559 down there. Or does it want a percent, where you would have to round to like 55.9%? Or, you just have to be on the lookout for format that it wants. All right, so that shows you how to use the website, how to process just what it means in general. Let's suppose we get a question about the standard normal distribution. So right here, okay? If you get a question about the standard distribution, then it means you would have to realize, it won't even tell you this, you would have to realize that you would have to change the mean to 0, because remember I told you if we're already talking about z-scores, the mean is 0, and the standard deviation is assumed to just be a distance of 1. So you would change this to 1. So let me even show you that if I go put in a z-score of 1.47, that I'm going to get the same answer. Like, let me go below and put in 1.47 and press enter. That is really the same question as when I showed you what happened to a weight of 192, because all it's doing now is standardizing everything into z-scores. And you see the display of z-scores here. But you basically are getting roughly the same answer. So if you get questions that are already in z-scores, rather than in original values like weights, heights, and whatever, then you just have to realize that the mean and standard deviation are 0 and 1 if the number is already a z-score. In other words, it's already assumed that the numbers have been standardized. So that would also be something that you might need to be aware of when you're working on your homework this week. Then another thing is notation. So if you see notation, let me actually erase this now. So a little while ago, I told you that let's suppose we assume male weights, adult male weights are normally distributed with a mean of 170 and a standard deviation of 15. That information may be presented to you like this. It may show a capital N, then parentheses, a 170, comma, and then a 15. When you get this notation, the N is telling you that you're dealing with a normal distribution. So all of these rules and stuff, probabilities that we're going over apply. The website applies. The front number that it gives you when it uses this notation is always the mean, and the second number is always the standard deviation. So basically, this is another way of giving you that same information, just not in words. It's giving you that same information, but using notation, sort of universally accepted notation. So you just have to know that that's what that means, and then go ahead and work the problems according to the same way I showed you. I mean, you would come over here and make the mean, change that to 170, change the standard deviation to 15, and just work your problems out. And then finally, so in other words, the formula that we used right up here is assuming that we are dealing with a normal distribution of individual male weights, individual males, so that the value was just one male, individual male's weight. And we worked it out and were able to get percentages above, below, and in between certain individual male weights. But for a big part of the course, when you're going to be doing hypothesis tests for means, you're really going to be looking at not a distribution of individual weights, but you're going to really be looking at distributions of sample means. So like when you take a sample of males, how do we expect the means of the samples to behave? And in fact, the last part of your discussion this week, we'll talk about, suppose you have a sample of, and I think it's 40 people. So this is where you're going to have to take this into account. Sample means, so like if I were to draw a picture of individual male weights, it might look like that. But when we take samples of, a bunch of males, let's suppose I took a sample of 50 males. If I calculated their mean weight, then the means would not be as spread out as individual male weights. I mean, to be logical, some males are very, very, very thin and can weigh as low as like 120 pounds. Some males, much heavier, can weigh 300 pounds, something like that. Big football players probably can weigh in the 300 some pounds. So those are individual, that's illustrating individual variation. But when we take samples of 50 men and average out their weights, we're probably not going to get as low as 120 or as high as 300 something, because we've got 50 males. So that variation is contained in the sample, and the average would head more towards the center mean weight. So what that means is means, so I'm going to use the symbol X if I were talking about this top distribution, because X is the symbol for individual value. But if I'm talking about X bars, which is the symbol for sample means, then sample means are not as spread out. They're still centered at the true mean. The mu would still be in the middle. But it's the spread that's not as large when we're dealing with means of samples. So what you need to realize is you'll be learning about standard error, which is the standard deviation of the distribution of sample means. And it is lower than the standard deviation, but yet it's related. So standard error is to take the standard deviation of the individual values and divide it by the square root of n. All right, so what that means is if the standard deviation were 15, and let's suppose I took a sample of 50 males, then the n would be 50, that's my sample size. So that the spread of the sample means, and I'm putting this in my calculator, 15 divided by the square root of 50, that's roughly around like 2.121. So if we're talking about sample means, they are not as spread out as individual weights. Individual weights had a standard deviation of 15. Sample mean weights have a spread of standard deviation of 2.121. We call that standard error. So that now if you got a question that said calculate the z-score of the 100, what did I have, 192, I think. So if I got a question where I had to calculate the z-score of 192, but assume that that was the mean of an entire sample, not just an individual person's weight, Then I would do, to get the z-score for that, I would do 192 minus 170, but I would use this standard error for the denominator. And let me put that in the calculator. All right, I am now getting a z-score of 10.372 roughly, or really 10.37. Okay, what that means is 192 for a sample mean would be way out there on the bell curve. So to kind of illustrate what's going on, it's really imagining these two different distributions here. All right, for an individual male, the weight of 192 was not really all that necessarily all that unusual. It was like right in here kind of. But if that had been the mean of an entire sample, that would have been way out here on the tail. Because when you get z-scores beyond -3 and 3, it means you're way out there on the tail. What that means is most means of samples of men would be much closer to the 170 than 192. So while 192 is not all that unusual for an individual male's weight, it would be unusual for the mean of an entire sample of men. It would be on the much higher side than we would expect. So you just have to be on the lookout for both of these in the discussion and just pay attention to whether we're talking about an individual or a sample to help you with that. And I believe hopefully that should be enough to get you through what you need to for the discussion, definitely, and then also help you get through those calculation problems in the homework where you can just come over here and use the website to make it really quick and easy to calculate areas above and below and between values in a normal distribution.